All right, hello SM1 honor students. Today we are going to go over our lesson 2.4. The content objective is to derive the explicit rule for an arithmetic sequence given a table, graph, or word problem. Explain, and then the learning objective is explain how a table and graph of a sequence are related to one another. So we want to use tables to be able to construct functions, and we also want to be able to construct functions from graphs. So if you remember, an explicit rule is just where we're able to use a sequence and formulate a function from that. So for example, if I look at this table here of numbers, this table shows the balance, the function of n, in dollars of a savings account after n months. So every time you see n is a month, okay? So we could have 1 month, 2 months, 3 months, 4, or 5. And you'll notice that in the first month, we put $180 into the account. And then every month after that, you can see that the account is going up by some value. Now, if we look at the original account balance of $180, you'll notice that when we go from the first to the second month, the difference is $70. So we added $70 to that first amount. And then you'll notice as we go to the third month, you'll notice that it goes up once again by $70. And you'll notice that this sequence, that's why we call it a sequence, because it's happening over and over again. Every time we go to the next month, it's simply $70 more than the last month. So we want to have a function that's going to express for us exactly what's happening from month to month, but we don't want to have to do this addition each and every time. Like, what if we wanted to know how much money there's in the account after 10 months or 12 months or maybe even 30 months? So we'd want a function that would show that. So for this function, we can see that in the first month, we have $180. Okay, that's our starting amount. We can never really go lower than that. And to that, we want to add $70, but we want to add $70 each and every month. So that's going to be 70 times n minus 1. You might think, well, how did I know to put n minus 1? Well, let's think about the logic behind that. If I take that first month, okay, and the months are n, if I take that first month and I put it in here, 1 minus 1 is 0. 0 times 70 is 0. So 0 plus 180 is going to be $180. But now if I were to put in, let's say, the second month, well, that's n is equal to 2 now. So if I put 2 in, 2 minus 1 is 1. So then 1 times 70 is just going to be 70. And 70 plus 180 is going to be $250. So that tells me how much money I have after that second month. And so it doesn't matter what month I put in, it's always going to give me the amount of money that would be in that account after that month. So let's apply that to what if n was 12? So what if we wanted to go to the 12th month? 12th month, which is not represented on this table. So we could do that by writing our function equation again, 180 plus 70 times 12 minus 1. So if we do that, we're going to have 70. So 12 minus 1 is 11. And so then we're going to have 11 times 70. And that gives us $770. And then we add that to 180. And so what that tells us is that when f of n is equal to 12, we're going to have $950. Okay? So then the question down here then asks, what does this represent? Well, what this represents is that in 12 months, he will have $950. Okay, so it's pretty simple, really, if we just think about how this data is changing over time. So let's try that again. Let's try to construct an explicit rule in function notation for the arithmetic sequence represented in this table. So the table shows f of n, the distance in miles from the store after Mila has traveled for n hours. So n again, n, 1, 2, 3, 4, these represent the hours that she's traveling. And if we look at this sequence, we notice in the first hour, she travels 27 miles, okay? And then by hour 2, she's traveled 36 miles. So then the question is, what's the difference here? What's the difference between the first hour and the second hour? Well, the difference there is 9 miles. And you'll notice as I go to each of these, the difference, again, is 9 miles. So that means this is increasing by 9 miles. So a good function of this would be start with what we know. We know that it's going to start out at 27 miles, plus it's going to gain 9 miles every n minus 1 hours. So every n minus 1 hours, it's going to go up, okay? And so now, if we want to solve, well, where would she be after 14 hours? And we can put that into the function, 27 plus 9 times 14 minus 1. And so 14 minus 1 is going to be 13, so we take 13 times 9, and then we add that to 27. So the function, this function at 14 hours, she's going to have traveled 144 miles. So the function gives us that amount. And we don't have to add 9 over and over and over and over again to get that. The function's going to do that for us through the process of multiplication. So what does this represent? Well, again, it represents that 14 hours, Mila should be capitalized, will be 144 miles from the store. So that shows us how we can use this arithmetic sequence function to figure out how far she's going to be. Okay, so let's move on to the next problem. So we've got another sequence here. So construct an explicit rule in function notation for the arithmetic sequence represented in this table. This table shows the total cost in dollars of purchasing n battery packs. So n represents how many battery packs we're buying. So we could buy 1 battery pack or 2, 3, 4, and so on and so forth. So again, we want to look at what's the difference from one sequence to the next. And the difference is we're adding 7. Okay, these are very, very simple sequences because we're just adding. So if we want to figure out what would the function look like for this, start out with our starting amount, okay, $7.90 plus $7 times n minus 1 battery packs for each time we buy a battery pack. And so now we want to know how much is it going to cost if she buys 24 battery packs. So we've got $7.90 plus 7 times 24 minus 1. So 24 minus 1 will be 23. So we take 23 times 7 and then add that to 7.9. If we are solving this function for 24 months, we'll find that it is $168.90. Okay? So what does this mean? Well, what does this function mean? Well, it means that 24 battery packs cost $168.90 because the function tells us that that's how much they'll cost by putting in the number of battery packs that we wanted. So let's apply the same concept of an explicit rule using a sequence to a graph. So we have a graph here. This graph shows the number of stamps, f of n, that Eric has in the nth month. So we don't, we could pick any month. We could pick 3 months, 5 months. We could pick 80 months. It really doesn't matter how many months. The graph is going to allow us to come up with a function that's going to allow us to solve for that. So use the graph to construct the function model for the arithmetic sequence and use the model to find the number of stamps Eric will collect in the nth month. So we've got a data table here. Let's actually fill in this data table real quick using the data that's here in this graph, and then we can use that to build a function. So you notice in month 1, if we follow this up, Eric has 35 stamps. And then in month 2, if we follow it up, Eric has 50 stamps. And then in month 3, we follow it up, Eric has roughly 65 stamps. In month 4, he's got 80. And then in month 5, he has roughly 95 stamps. So now we have to ask ourselves, what's happening from month to month? Okay, so in the first month, he has 35 stamps. And then in the second month, he has 50. What's the difference there? Well, it's going up by 15 stamps. So now we look at going from the second to the third month. Is it the same jump? Is it going up by 15 stamps? And the answer is yes, okay? Each time it increases by a month, he gets 15 more stamps. So he's getting roughly 15 stamps per month. So then our function should be his original starting amount of stamps from month 1, 35, plus 15, because he gets 15 stamps every month, times n minus 1, n being the number of months. And so now we can figure out how many stamps he's going to have any number of months. And so let's look at that on the next page. All right, at the top here we have how many stamps will he have if we're looking at 9 months. F of n is 9 months. So we put in 35 plus 15 times 9 minus 1. 9 minus 1 is 8. We take 8 times 15 and then add that to 35, and we see that at 9 months, he's going to have 155 stamps. And if we were to increase the size of that graph, and if we kept graphing, we would see that at the 9th month, that's where that graph would go. It would go to 155 stamps. Okay, so in 9 months, he's going to have 155 stamps. All right, so let's look at some more graph examples. Here's a graph that shows, the graph shows the height in inches of a stack of boxes on a table as the number of boxes in the stack increases. Write the explicit rule and function notation, then find the height of the stack with 9 boxes. So what is this graph telling us? Well, at the bottom, the x-axis, each of these numbers, that tells us how many boxes we have. So here we have, 0 boxes, 1 box, 2, 3, and obviously it starts at 1 because it doesn't really, we're not going to have anything if we have 0 boxes. We're not going to have any height. But if we have 1 box, it is 38 inches in height. And then we've got 2 boxes, 3, 4, 5, 6. And as we start stacking these boxes, we can see that there is a climbing difference. So you can see as we go from this one to this one, the difference between 38 and 57, well, it's a difference of 19 inches. And then 57 to 76, also 19 inches. 76 to 95, also 19 inches. So this is increasing. Every time we add a box, we add 19 inches to this. So if we want to write a function f of n should equal our beginning amount, 38 inches, plus 19 inches each and every time times n minus 1 boxes. And so now this will give us the height of the boxes regardless of how many boxes we have. And so then it wants to know how big will the stack be if we have 9 boxes. So f of 9 equals 38 plus 19 times n minus 1 boxes. So n minus 1 is going to be 8. 8 times 19, and then we add that to 38. And f of 9 is going to equal 190 inches. So again, what does this mean? It means that 9 boxes is 190 inches tall. That's what this is telling us. All right, let's look at this next problem. Sorry, let me slide this over. So Quinn begins to save the same amount each month to save for a shopping trip. The graph shows the total amount she has saved after each month, n. So n is going to be the number of months. Write the explicit rule and function notation. What will the total amount Quinn has saved after 16 months? Okay. So again, if I look at the data that's in the graph, x-axis is the number of months. We could have 1 month, 2, 3, 4, 5, 6, 7. They could keep going. And then we have the total amount that she has saved. So at 1 month, she has $330. If I go to the next month, it's $400. Well, what's the difference there? Well, the difference is $70 more. So she's added $70 to her savings. If we go to the next month, also $70. And then the next month, also $70. So she's saving $70 every month. So now if we want to write a function for this, f of n should equal, we have to start with her original amount that she put in, $330 in month 1, and then how much it's going up by each month, 70 times n minus 1. And I just want to reiterate why this does need to be n minus 1, because we want this function to work for all months, not just the months moving forward after the first month, but this needs to work for the first month too. If I put month 1 in here, that'd be n is 1. 1 minus 1 is 0. 0 times 70 is going to be 0. And then 0 plus 330 is 330. So that actually still gives us the amount of money she had on the first month. And then moving forward, it's going to give her all those other successive months because it's going to add $70 each and every month. So now the question was, how much will she have saved after 16 months? So let's put that into the function. F of n, instead it's f of 16, will equal 330 plus $70 times 16 minus 1 months, okay? So we're going to take 16 minus 1, that's 15. 15 times 70, and then we're going to add that product to 330. And when we do that, we find that when the function f is 16 months, she'll have $1,380. So after 16 months, she'll have saved $1,380, okay? So that's what this function helps us with and tells us that information. All right, guys, so we're almost there. We just have a few more examples to go over, and we're going to apply these rules. So we're going to build our own here. So this time we don't really have much data to go off of, but we do have enough information to still be able to build a function. So the example is the odometer on a delivery truck reads 92,556 miles. At the end of the first day of a new delivery route, the truck's new delivery route is 73 miles each day. If this pattern continues, what will be the odometer reading after the 7th day? So we want to talk about a few pieces of information. First of all, what's f of 1? In other words, on day 1, what's the odometer reading? And it tells us in the problem. It says that before it starts this delivery on day 1, it starts out at the beginning of the day with an odometer reading of 92,000 556 miles, okay? So we know this. This is information that we know. And then we want to know, what's the common difference? When we say common difference, we're talking about what's going to happen each and every time we change f of, n. And the common difference here is that we're going to add 73 miles, okay? So that's what's going to happen. We're going to add 73 miles each and every time. So now we want to talk a little bit about the recursive rule, which you guys went over in your notes the other day. So the recursive rule is a little bit different. We want to know, what's going to happen, each and every time. And so the recursive rule here would be that the function f of n would equal the function of n minus 1 plus 73, the difference in miles. So essentially what this is telling us is that every time we change a day, we're going to add 73 miles. Okay? That's what the recursive rule is telling us. So if I had one day, 1 minus 1 is 0, and so I'm not going to add 73 miles. So on day 1, I'm starting with my original mileage. But then if I go to day 2, 2 minus 1 is 1, and so I'm going to add 73 miles. So if I want to write this in the explicit rule format, which is the way that I think you guys are probably going to understand a little bit better, we've got f of n is equal to, well, what's our starting amount? It's 92,556 miles plus, well, how much does it change by? Well, it changes by 73 miles each and every day times n minus 1 days, okay? So we can put any amount of days in there, and then we're going to multiply that by 73 miles, add it, and we'll figure out how many new miles we have. So if we go to the example, what's f of 17? Well, it's going to be 92,556 miles plus 73 times 17 minus 1. So 17 minus 1, again, is going to be 16. Take 16 times 73, add that to 92,556, and what we find is that if n is equal to 17, then the function of n is going to equal 93,724 miles. Okay? So that's what that's telling us. All right? Okay. So now moving on, we move up here. This is your turn, but I'm going to go over this with you. Okay? I suggest maybe pausing the video here, trying these two out on your own, and then unpausing the video to see how I solve it and see if it lines up with how you're doing it. Okay? So the example here is Ruby signed up for a frequent flyer program. She receives 4,000 frequent flyer miles for the first round trip she takes, and then 1,400 frequent flyer miles for all additional round trips. How many frequent flyer miles will Ruby have after 6 round trips? So we want to talk about first, what is f of 1? Okay? In other words, if n was 1, what's going to be the function? The function is just simply going to be the amount of miles she gets right from the start. She gets 4,000 frequent flyer miles. And so now the question is, what's the common difference? Well, the common difference is how much is going to be added after that. So after the 4,000 original miles, she's going to get 1,400 frequent flyer miles every time she flies. So we put 1,400 in for the common difference. So now our function is going to be f of n equals 4,000. So notice the function is always f of 1 goes into the first spot in the function plus the common difference, okay, times n minus 1, okay, what's happening over those times. So now we want to know what's going to happen if she makes 6 round trips, f of 6. So it's going to be equal to, again, f of 1, which is 4,000, plus 1400 times 6 minus 1. 6 minus 1 is 5 times 1400. Add that to 4,000, and we find that f of 6 is equal to 11,000 frequent flyer miles. Okay? All right. Last example. A gym charges each member $220 for the first month, which includes a membership fee, and a $50 per month for each month after that. How much money will a person spend on their gym membership for 6 months? So again, we want to identify what's f of 1? Well, it's that initial membership fee, $220. And then what's the common difference? It's going to be the $50 everyone has to pay after that. So then our function, f of n, is going to equal f of 1, the $220, plus the common difference times n minus 1. And so now we want to know how much is the gym membership going to cost after 6 months. So f of 6 is going to equal, again, we put in f of 1 for the first place, $220 plus $50 times 6 minus 1. 6 minus 1 is 5. 5 times 50, 250 plus 220. So f of 6 is going to equal $470 for that 6 months of the membership. Okay? So hopefully this makes sense to you guys. We're definitely going to do more problems in class, more examples, and we'll make sure that you guys understand this. So talk to you later. Bye.